Okay, so let's continue from where we left off last week, last class. What did we did input matching, we did output matching, the output load, and then we looked at stability, right? Okay, so let's continue from there. I'm hoping to finish off LNAs today. In case there's a little bit left, we'll take it up next week. Okay, but you'll have definitely at the end of today's class, you'll have enough to start your projects. Okay. Okay, so what did we look at last class? So we looked at, okay, obviously input matching, right? So just remember, input matching or output matching is sometimes also called return loss, S11, S22, quite often called return loss, and it's nothing but 20 log and similarly for output matching, okay, something similar you'll have, okay. And remember, your input and output matches, in case you have an LNA, where you need to do both matchings, there will be some dependence. Okay, there will always be some dependence because you have GM the forward way, CGD for the reverse way. Okay, so you'll always have some dependence. Now, in the present LNA project announcement, what I have done is I have asked you to match both the input and the output. Okay, now that would be the case for a discrete LNA. Or either a discrete LNA where your LNA is a separate block by itself and you have to do 50 ohm matching everywhere, or the other option is, remember we looked at the output of the LNA you might require some kind of filtering, okay, and usually such kind of filtering would be an off chip filter. If that is the case, you again have to do 50 ohm matching, but suppose you don't, okay, if you don't have to do that, then you don't do matching at the output, you would include the load of the mixer as part of your tuned circuit, okay. So that way you wouldn't you would have to worry about S11, but there's no longer a problem with S22 and so on. Okay. Now we are still trying to decide whether we want to do output matching or not. We'll let you know by Monday. Okay. If it is not required, I'll change the project and change the deadline accordingly. Okay. We'll also put up the tutorial by Monday.
So you have asked for a Q of 10.
Yes, and I'll also change the ascetic file. Okay, such that so make sure to download it again. I'll update it by this weekend, such that you'll be able to get better queues very easily. Okay, I'll just make it very standard. You can easily get a queue of 10. Okay. Okay, so what did we see? CGD was a problem, right? Okay. So how do you get rid of CGD? Okay, so one very brute force, I guess you could call it a brute force method, is, so let's say you have CGD. So one of the things you have learned is, let me move it down a little. So one of the things you have learned is we use resonant circuits all over the place, right? So let's say we can tune out this with a parallel inductor, but of course you can't connect it directly. You need a large capacitor. Let's call it CB. Okay, you can do something like this. You can use your inductor to tune out the gate drain capacitance. So that is one way. It's kind of a brute force way, but you can do it. The thing to remember is, obviously, as we know now, these inductors have parasitic capacitors. You have capacitors which have bottom plate capacitances, parasitic capacitances. So all of this will load your input node. Okay, and obviously the second thing is, we're not even talking about the area, right? So you saw that it's 200 microns by 200 microns. It's just huge. You can't just afford to add an inductor anytime you want. Okay, so the other easy way, so this is the first way. Okay, tune out your CGD. Okay, the other way, of course, is the more commonly used way, is the cascode. Right, so you effectively isolate your input from your output using a cascode transistor. Okay, so just remember that if you do this, so let's say quite often what you might want is you might want a different size for the cascode. It doesn't, your starting off size will be the same as your main transistor, but at the end of your optimization it may not be the same. You may not need a much larger transistor. Maybe you can make do with a smaller transistor. Okay, the thing to keep in mind, maybe you want a larger length for the cascode, but the thing to keep in mind is you will have some parasitic capacitance at this node and you want to minimize that capacitance. Okay, why? Because obviously your signal is going to get diverted through that. Okay, and the other thing to, what would you do with the gate of the cascode? Typically you would connect it to VDD in most of these cases. That's not a problem. You want to get maximum headroom for the main amplifier. Okay, so finally, so we have, or we think we have our common source amplifier, LNA. Okay, and of course you're going to drive it with Vs. This is your output. You have some load capacitance, CL, and you're going to try to make CD much larger than CL. We talked about it last week. Okay, so this is what a typical common source amplifier would look like. And if you see, in many cases, this is probably the one of the best kinds of amplifiers. We saw that the common source MOSFET has a pretty low Fmin. If you look at the Fmins you can get from this, we looked at the MOSFET 2-port parameters, right, with the common source. So you can get very low Fmins, 0.6, 0.7, somewhere around that. Okay, even for a long channel. Okay, and now you add the cascode, you have got rid of your stability problems, or at least to some extent. Okay, you have, your common source has a lot more gain. Okay, so this is pretty good. The only difference is you're doing a narrowband match at the input, and that is, as opposed to a common gate structure which would have a wide band. There are some cases where you would want to choose a common gate. For example, if you look at the noise figure versus frequency, okay, remember that the noise figure of a common source is proportional to omega over omega t. It's not 3 dB actually. No, that is only if you are using a resistance at the input, right? For this one, Fmin is actually much smaller. It has some form 1 plus something, a lot of constants times omega or omega t. Remember that? We'll come to it later in today's class also. Okay, so it increases its frequency, maybe some kind of nonlinear increase. Okay, and if you look at a common gate, so this is a common source. If you look at a common gate, it starts off much higher, but in a given technology, beyond a particular frequency, of course, common gate will also increase, but much lesser, okay, and it will increase at a much higher frequency. You might find a point where common gate works better, but you have to actually go pretty high in frequency to achieve that. Okay, because remember we calculated the common gate last week, it is 1 plus gamma over alpha, right? So that is actually high enough. We saw minimum is 2.2 dB, so it's actually much higher than a common source. But this the frequency at which a crossover occurs actually maybe tens of gigahertz, maybe 20 gigahertz, 30 gigahertz. Okay, at the typical frequencies of interest, you may not worry about the common gate too much. Okay, so let's look at some other quantities of interest. Actually, so we did input match, output match, and we did stability. So let's look at voltage gain. AV. So we already know this, right? So it is the effective GM times the parallel resistance of the tank RP, right? And we also know this is okay. So that is the effective voltage gain. And what we are doing is we are obviously neglecting the output resistance. Now that we have added a cascode, the output impedance of the amplifier itself actually gets even better. So it's a good approximation to use just RP. Okay. Now for any 2 port, you can also define what is called transducer gain. Or transducer power gain, which is called GT. And your GT is defined as power delivered to the load over, actually it's the maximum power available from the source. So we'll call this P load over P available S. Okay, we already know what P available S is, we've calculated this before. Yes. So let's assume we are working with peak quantity, so it's 2 Rs Vin over root 2 whole squared over Rs. So let's say your load is some YL. Okay. So we are talking about a case where input is matched. The maximum available power from the source is when the input is matched, but we don't have any constraint on the load so far. So the load can be anything. Okay. So what does this mean? Let's take the real part. So we'll take YL as some GL in parallel with BL. GL is real part of 1 over ZL. Okay, so if you look at the output, so you have the 2 port, so you have some AV times Vn. Okay, you have some R out here, which is RP in our case, and we have some ZL. Actually, that is not RP. That is RP, right? Okay. So what is your P load? Okay, it's V out squared over 2 times GL. Okay, so which is and obviously we can write V out as in terms of Vn because we know the voltage gain.
So why did you put RP in parallel?
RP is actually in parallel for if you look at the common source, it is actually in parallel, right? So the RP is the resistance of the tank and output impedance, it's actually in parallel. So you have
You say AV actually is
AV always include, AV actually included RP, remember that? AV is actually GM times RP. Okay, and we know V out is, yes,
you put Z as your AV will change.
AV will not change, AV is the unloaded voltage gain, right?
If I load it, the voltage is going to change the power transfer.
Yeah, which is why we are calculating P load in terms of ZL.
So V out will not be multiplied by V in.
Yes, so it will still be because RP is in parallel with ZL, right? So this AV times Vn will still be valid, just the power delivered to the load will not be valid anymore. That's all. Okay? What do you know about Vn? Actually, let's leave it in terms of GM. What did we calculate? GM times? Okay. V out is GM, now it is GM times RP parallel ZL times Vn squared, right? Okay, and so your GT is this over half Vs squared over Rs, right? Oops, sorry. Actually, this should be mod. Sorry, because ZL is actually imaginary, right? Times okay. This is your transducer gain, and this is true for any 2-port, okay, which has some certain gains and so on. Okay, so let's consider two cases. One case is, let's say the LNA is driving some output, like let's say a filter or something, some kind of off chip case, so in which case your output is matched. Okay, GM. So our ZL is just RP, right? ZL is equal to RP. And real part of 1 over ZL is nothing but 1 over RP. Okay, and this also happens to be the available power. Remember, available power was power available, at the load under match condition over power available from the source, also under match condition. Okay, so let's say you're driving let's say a mixer directly, and you have a capacitive load. What do you think your GT is going to be? What is the power delivered to the load? It's actually 0, because the input of the next stage, if it's capacitive, if it's a MOSFET, it's purely capacitive. Okay, or it will be almost purely capacitive. You will have some kind of gate resistance, which we usually try to minimize anyways. So it's going to be extremely small, which means in such a case, your transducer gain would be 0 or would tend to 0. Okay. 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 Well and good. So now we have found out the gain, power gain, everything. Now you will notice that when we talked about the design of the LNA so far, we talked about input match, output match, stability, everything. We never talked about power consumption. Okay, especially when we derived your minimum noise figure. Okay, so it's basically we didn't put any bound on your minimum noise figure. So if you try to achieve this minimum noise figure, you will find that the amount of power you will have to burn is huge. Okay, to hit this number. So what we need is some way to do what is called power constrained noise optimization. Okay, that is, you have a certain upper limit on power you can consume in your LNA, and you need to calculate minimum noise figure based on that. Okay, it will definitely be larger than your Fmin, but you want to know by how much, right? Let's say you are willing to give up a little bit on Fmin, a little bit on noise figure above Fmin, but you give a reasonable bound on power. Okay, now I won't go through the derivation. In fact, even the textbook does not go through the derivation because it's quite complicated, but I'll give you the result and I'll tell you a little bit about how he arrives at the conclusion. Okay, okay, so see, you can look at pages 380 to 384 in Thomas Lee's textbook. Okay, that has the slightly larger derivation. Okay, even he does not give the optimization portion. okay, because it runs into a huge polynomial which you need to solve, okay. But we'll just quickly go through what needs to be done. Remember, plus, so you remember this expression, right? We found out f equals f min plus in terms of gs minus g opt and bs minus b opt. Right? We talked about noise circles. Okay, so the first thing you assume is that the imaginary part is bs minus b opt is very small, so you can neglect it. So it's matched at least. Okay, the imaginary part is cancelled out, or at almost so. Okay, so then you define what is called, okay, so we'll define what is called q opt, okay, which happens to be g opt over omega cgs, and you can show that this is alpha times delta over phi gamma, okay. So don't worry too much about the derivation for now, we just want the final result, okay. And then you also define what is qs, which is the 1 over omega cgs rs, okay. So what you want to arrive at is an optimum width of the transistor, okay, given a power dissipation bound, okay. So the width of the transistor comes through omega cgs, because cgs depends on the width of the transistor, okay. So obviously qs will vary, so you want to find out optimum qs, okay. So now you can rewrite f alpha gm rs okay. So you can rewrite it this way, and this is the function you're going to minimize, okay, based on some constraint. And finally you get the value of qs. It turns out that the optimum value of qs, that is the power constrained value of qs, happens to be around 4.5. It's a q quality factor value, right? Happens to be around between 4 to 4.5, okay. This is omega C ox. So CGS is 2/3, right? 2/3 WL C ox. And you put QSP equals 4.5. Okay. QSP is the power constrained QS. So it is QS after you have optimized QS, after you have applied the power constraint. Okay. It turns out that if you use a QS of 4.5, you can get actually pretty good noise figures for a given power. Okay. And it happens to be fairly broadband with respect to bunch of parameters, width and delta, gamma, omega and so on. Okay. As well as the power consumption. As long as the power consumption is low enough, there happens to be an optimum width. Okay. So so we'll go through the design procedure next, right? How you would start off designing your common source LNA, and you'll see that this offers a good starting point for you. At the end of the day, your hand calculations are always going to be only a rough point to start from. You have to rely on the simulator, but you just have to do it smartly. Okay, you don't just start off randomly. You have some amount of work done before.
So that is W of P. Optimum.
Yes, optimum, power constraint, optimum width.
This side also W, L and C.
Omega. This is omega. That's why, yeah, trying to write it slightly differently. Okay. So it turns out your final expression for F min, power constraint F min, looks something like this. So you do, but you, okay, so what this means is this gives us a good starting point. You do have control over W, definitely, and your F min will vary, but it will vary, it's actually fairly insensitive to W, that's all, that's what it means. Okay, and if you remember your earlier F min, right, if you put in gamma delta values, you will see that it's approximately 1 plus one plus 2.3 omega over omega t. Okay, so if you actually look at some different values, right, so so let's take 4 values, 20, 15, 10 and 5. Looks something like this, and your F min P is not too bad. Okay, so this is, it's not too bad. You can see if you're, as long as you choose a properly normalized omega t or omega. Okay, so where does your power come in? Power comes in through your omega t. Okay, if you burn more power, you can actually get better omega t's. Okay, if you have control over the width and the current consumption, right? So you choose omega t based on that. Okay, and you can see that instead of just randomly, rather not increasing your power consumption, if you constrain it to some level, you can actually get pretty good. So 0.5 to 1.1 is like another half a dB, so it's not too bad. Okay, and of course this assumes no, not at all. Omega t is fixed. If you fix your size and current, omega t is fixed. Remember, it's just Gm over CGS. How can it be fixed? If you change the sizes, omega t will change. Right? If you burn more current, your Gm is going to increase, so your omega t is going to increase. Now, sorry? Why would CGS increase if you increase power? Yes, so let's say you take a given size, okay, it has a certain, and you burn, let's say 1 milliamp of current in a 10 micron by 0.13, okay, it has a certain GM, it has a certain CGS, it has a certain omega t. Double the current to 2 milliamps, what happens? GM goes up, okay, whereas CGS stays the same. So omega t will automatically get better, definitely you can. So when they talk about omega t for a particular process, what they are talking about is for a given size and given current consumption and so on, okay. Okay, so now let's come back to our our design procedure. So first, of course, we are going to determine W of P. That's the basic starting point. Okay. Okay, then you're going to choose an I bias based on your power constraint. you have some desired power dissipation, and you're going to choose I bias based on that. Okay. Next, you're going to determine LS. Okay. So the thing to remember is, obviously I have not put in the length of the transistor. I'm assuming that you're going to use minimum length because you want maximum FT, right? So I'm assuming already that you're going to choose minimum length, and you would normally want to do that if you want to hit minimum noise trigger. Okay. And once you have these two, so you know CGS, so then you can calculate LS, which is your source inductance to match, because once you determine I bias and W opt P, you already know your omega T. Omega T times LS is 50 ohms. So based on this, well, omega T times LS is RS, but in this case I have assumed it's 50 ohms. Okay. And of course, you're going to calculate NF min, right? That is something you will want to do once you know W out P and omega T. Sorry. Okay. Then, of course, you want to calculate LG such that your input is matched at the desired frequency. Okay. So now you have the transistor, and you're going to add the cascode most probably. Okay. Cascode adds a lot of benefits, so you're most probably going to add the cascode, and I'm assuming that you'll start off with cascode same size as your main transistor. Okay, that is given. So then next thing to do is choose the load. So how would you choose LD and CD? So you want maximum gain from your LNA. Let's assume you want a certain amount of gain. Okay, so you want to maximize. Let's say you want to maximize that gain. So you choose LD and CD such that you would maximize RP. Why? Why do you want to maximize RP? Because if you maximize RP, you know that your gain depends on RP, right? So you maximize RP, you can actually cut current and achieve the same gain at a lower current. That's all. Okay. Okay. And probably you'll need to iterate. Okay, definitely between steps, probably overall probably need to iterate, but that's okay. That's normal. Part of normal design procedure. Okay, and that's it, you're actually done. Let's say if you need to do an output match, so in a normal case, let's say if you're driving a mixer, that's it, okay, you're done. If you need to do an output match, then you know RP, so you need to transform it down to RL, which may be 50 ohms, let's say. So then what you would do is, you'd use some kind of L match or pi match or whatever, T match, whatever you want to do, and put a matching circuit at the output. And that's it. After that, you're done with the hand calculation, hand design. After this, it's up to the simulator to figure out. So the simulator gives you the noise figure. It will give you noise figure minimum, okay, for that condition. Okay. So you can find out how close you are, okay, whether you're optimized or not, and so on. Okay, that you can figure out. We'll put up a tutorial on Monday, and you should be able to get going. Okay. Now the other thing we didn't talk about at all was IIP3. Yes. It depends. Yes. So normally, okay, if you go to a differential topology, did I have a homework problem on this? No, right? So what you'll find is, if you go to a differential topology, it actually gives you better linearity, but the noise figure is the same. It won't give you. Yes, so that is common mode noise. So far, actually, if you see, so far we have not talked about common mode noise. We have not talked about supply noise. We have not talked about ground noise. Nothing. We have talked about intrinsic sources of noise. Okay, you are right. If you have a case where your substrate is very noisy, your supply is very noisy, in cases like that, you might want to choose differential topologies if it is absolutely necessary. But remember, it's actually a trade-off. What you'll find is your current consumption may be in several milliamps. So obviously, if you go to a differential topology, you will end up burning, let's say it's 5 milliamps. Differential means 10 milliamps. Okay, so you may be worried about power consumption. So if it's absolutely necessary, you will go for it. Okay, if it is not, you may not want to go for it. You might end up using a transformer at the output of the LNA to go into the mixer, in case your mixer is differential. Okay, but both things are possible, definitely. Yes. Yes, which is why you maximize RP to get maximum gain. Okay, so what you would do is, this is what you would do. So let's say you go through the step for now, you have maximized RP. How would you maximize RP? So you have an RP component from the LD. Let's say in this case, in our case, it is coming only from LD. Okay, because we are assuming that we have ideal capacitors. Okay, so and typically the Q of capacitors is much larger anyways. Okay, so let's say you choose an inductance of 1 nanohenry. I gave you, I asked you to choose Q of 10. So that will give you a particular parallel resistance. Okay, based on that you put that in and you see if you get enough gain. If you don't, you will probably have to use 2 nanohenry or 4 nanohenry and so on. You will have to increase the inductance. But remember, when you do that, your CD also keeps coming down. Okay, which means you may not be able to tune out the load. It becomes more sensitive. So you have to choose that carefully. Okay, but once you do that, definitely you're right. Once you choose omega opt and I bias, your GM is fixed, your omega T is fixed. Okay. Okay. So the other thing we didn't talk about was IAP3. Okay. The reason is, obviously we know that the MOSFET is not it's a short channel MOSFET. It doesn't behave in a square law and so on. So definitely so it is not that easy to calculate the IAP3, do a hand calculation, because it's going to be quite far off from your measurement. Okay, from your simulation or measurement. So what you do is you go through this design procedure. Okay. And you come up with an simulate your IAP3. See if it looks good. Okay. If it doesn't look good, then what you would do is, the only way to improve IAP3 is to increase VGS minus VT. Okay. IAP3 is related to VGS minus VT. Okay. So you increase the VD-SAT of the device, then your IAP3. So you increase I bias. VGS minus VT increases. Okay. IAP3 will improve. Okay. Okay. But there is one more thing you have to keep in mind. Remember, your short channel effects depends on VGS minus VT. So you increase VGS minus VT, you are going deeper into short channel regime, which means, remember, your alpha quantity was GM over GD naught. For a long channel MOSFET, it's 1. For a short channel MOSFET, it decreases from 1. Here, for example, we assume 0.85. It will reduce even below. Okay, it will keep decreasing. So what that means is, if you look at your noise figure, it is inversely proportional to alpha. So as alpha reduces, your noise figure will increase. So just keep that in mind. Okay. Sure, but okay. So remember that I bias, if you increase, FT will actually get better, which means your noise figure, effective noise figure will go down, right? Because your noise figure is inversely proportional to FT. But alpha also reduces. It depends on how much each one reduces by. Okay.
How about the swings?
What swings? Okay. So obviously, what you'll have to do then is you'll have to change RP. If you're having too much swing at the output, you'll have to change RP again. Tune RP to reduce it such that you have just the right amount of gain and right amount of swing. Okay. Okay. And
What is the maximum value of
maximum what?
maximum input power for
Maximum input. Oh, I see. So you're asking about the signal coming into the LNA. That will typically, the max, okay. The maximum value would be, I don't have a number off the top of my head. IAP3 will typically be like minus 10, minus 5, sometimes 0, okay, not higher than that. The maximum signal, I don't have a number off the top of my head. The minimum signal coming in will be in like microvolts.
Because if it is like no 2 microwatt for 100 dB per this, and if it is like 2 or like 50 dB up from
It could be. It could definitely be.
yeah,
Okay. It could be. It could be as high as like minus 20, minus 10 dBm.
even if you expect a gain of 10 on the LNA, you don't have much requirement on the output swing. Like it never go to rail operation.
That's right. Yeah, that's for sure. It will never go rail to rail operation. But I assumed what he was asking is because the output swing increases, you could have it could impact linearity again IAP3 in a second order way, right? So that is what I assumed you're talking about. The swings at the output, you're right, will never go to volts or something like that. That is for sure. Okay. This is not like a power amplifier. Swings will be in like very small numbers. The only thing you could see is the swing affecting your linearity. Maybe if the swing gets high enough.
And in the practical case, whether people will dynamically change the gain or will keep the constant gain.
It will not be. It won't be dynamically. It will very rarely. Yeah, I don't know of any case where it will be changed dynamically. However, you would have gain steps. Okay, but that wouldn't happen online. It would happen, once you start transmitting pretty much again. So what you do is you could have different gain steps. There are cases where when you are very close to the transmitter, you may not require so much gain. So you'll have maybe gain steps of maybe 20 dB all the way down to maybe 5 dB or 3 dB. Okay. Obviously, when you're closer, your signal is larger. You don't need such a good noise figure from your receiver. Okay. So, but then what that means is then you would once you detect such a large signal, you would automatically set your LNA to a low gain state. Yeah, but it's a low noise amplifier. You're designing for low noise, right? I mean, we just spent the last 2-3 weeks, designing the LNA based on 2-port noise and minimization of the noise, right?
The noise minimization, what you are doing, that is actually that's why you are calling it filter. Otherwise, it's just like a common source of common filter.
Yes. Well, okay. So if you just take any random common source, it will definitely have a much higher noise figure. Okay. What we are doing special here, of course, is we are trying to make sure that input is power matched, of course, but that has nothing to do with noise. But we are also trying to make sure it is close to being noise matched. That's the reason. See, remember we designed, looked at a 2-port. Okay. We found out what the noise match condition is and the minimum noise figure of the 2-port itself. And now we have chosen, let's say, W of P based on NF min or something which will lead us to a noise figure which is close to NF min. Okay. If you take any random common source amplifier, it will not be anywhere close to NF min. Okay. Okay. Let's see, what else did I want to do to today's class? Okay. I guess the other things you can look at are things like current reuse. Okay, so there are multiple ways to do it. I'll just show you one quick way. So this is GM times Vn. You can try to use something like this, for example. Sorry. More like an inverter kind of. So effectively you are reusing the current to get double the gain.